So in the last few videos, we've been talking about photosynthesis and the process that it goes through, the non-cyclic photophosphorylation and the Calvin cycle. I mentioned that in the non-cyclic photophosphorylation, we can actually go through a cyclic photophosphorylation cycle. And the reason being is now that we kind of have an understanding of how the Calvin cycle works and the amount of ATP that is required versus how much ATP is actually created in the non-cyclic photophosphorylation, we could see possibly where and why we would need to have the chloroplast switch to a cyclic photophosphorylation. The reason why that it switches over is because it needs to produce more ATP. So to create one glucose molecule, we need a total of 18 ATP. The problem is that in the non-cyclic photophosphorylation, only one ATP and one NADPH is produced as two electrons pass through the whole electron transport chain. So we're making one ATP and one NADPH, but we're using a total of 18 ATP and 12 NADPH. So we use ATP much faster than NADPH. The non-cyclic photophosphorylation can't keep up, and this is why sometimes it turns into a cyclic photophosphorylation. The goal of the cyclic photophosphorylation is to produce more ATP, and the reason why we need to make more ATP than NADPH is because the Calvin cycle uses more ATP than NADPH, so ATP gets used a lot faster. How does cyclic photophosphorylation go to switch into the cyclic process? What happens is that it actually switches and does not use photosystem 2. When those electrons go to photosystem 1, the ferredoxin will normally take it to make NADPH. Instead of this happening, what's going to happen is the ferredoxin is going to go take those two electrons back to the B6F complex in the ETC, and those energizing electrons are going to again help to make the electrochemical gradient to help make more ATP. So this process only makes ATP. So when we're talking about cyclic photophosphorylation, it's only going through the photosystem 1, and that process is happening over and over again to keep continuing to make more of that ATP. So we can see here in our photosystem that electron gets energized by the photon of light. Then that electron is going to move to the electron acceptor, which then goes to the electron carrier, our ferredoxin. Instead of the ferredoxin taking it to the NADP reductase, which is the enzyme that's going to turn NADP into NADPH, it's actually going to take, so ferredoxin itself is going to take that electron right back to the B6F complex. So when it brings it right back to the B6F complex, it basically allows for more hydrogen ions to be pumped into the lumen of the cell, which will then go through the ATP synthase in order to create more ATP in the stroma. So, and then from here, the B6F complex will then take that electron back into photosystem 1, and again, that cycle continues. So the cell is able to turn this process on and off to go either into a cyclic photophosphorylation, or it can turn it back into a non-cyclic where it goes through the whole process using photosystem 2 and photosystem 1.